Welcome to the lecture titled Model Free Controller Design. In this lecture, we will discuss about the tuning of PID controllers without obtaining a transfer function model. So, the parameters of the controller will be explicitly expressed in terms of the limit cycle output parameters. Ziegler and Nichols in 1942 suggested tuning method based on the concepts of the critical point on the process Nyquist curve, and since then many more methods have been proposed and suggested to design controllers without finding the transfer function models. One such method will be discussed in this lecture, and the advantages of the method we are going to discuss in this lecture estimates the critical gain and critical frequency more accurately than the existing conventional relay auto tuning methods, because the relay will not be an ideal relay alone, it will be connected in series with some integral controller, thus giving us certain advantages. Again, the controller will remain in operation throughout the operation of the closed loop control system. Auto tuning method gives a symmetrical and smooth limit cycle output in the presence of static load disturbance and measurement noise. Because of the integral controller along with the relay or the modified relay, because of the presence of the modified relay, what we will have clean, not only clean limit cycle output, but also the limit cycle output not disturbed by any static load disturbance. Now, also the method does not require prior information about the process. So, we need not find the transfer function model, rather the parameters of the controllers will be functions of the transfer function model parameters, or indirectly speaking, directly using the limit cycle parameters we shall find explicit expressions for the parameters of a PID controller. So, no need of finding the transfer function model and no more process information is required for tuning the parameters of a controller. Needs to design only two controller parameters. By this method we are going to discuss, we need to design only two controller parameters, namely a proportional gain and a derivative time constant from the modified relay experiment. So, when a controller of the form GCS is equal to Kp 1 plus 1 upon TIS times 1 plus TDS is considered, a series form of PID controller is considered. What I mean by the two controller parameters, we are going to find explicit expressions for Kp and Td. Of course, Ti will be also found ultimately, but we need to design only two controller parameters such as Kp and Td, and we need not go for Ti, because Ti will be set during the relay experiment. Let us see in detail what type of auto tuning scheme we have. So, initially what is done, a modified relay is employed to induce limit cycle output. So, the switch is connected to this point and limit cycle oscillation or relay test is carried out. Now, the modified relay is made up of an ideal relay. So, the modified relay is made up of an ideal relay in series with a integral controller. So, what is the form of the integral controller? GCNS will be of the form 1 plus 1 upon TIS. So, when this integral controller is connected in series with an ideal relay, we do get the modified relay, and when the modified relay is connected with the process in closed loop feedback, then limit cycle output is obtained. So, limit cycle output is obtained. So, after obtaining the symmetrical limit cycle output for symmetrical relay, we will make measurement of the peak amplitude AP and the period Tu, which will give you the angular frequency omega equal to 2 pi upon Tu. So, the frequency and peak amplitude of the limit cycle output will be measured. Then, based on the information of frequency and peak amplitude, we shall set the parameters of the controller, and then the switch will be moved to this point for normal operation of the closed loop system. So, that is what we are going to do. Now, we have to find explicit expressions for parameters of not only the I controller, but also the remaining PD controller, which will be added to this, giving us a controller PID controller of the form GCS is equal to Kp 1 plus 1 upon TIS times 1 plus TDS. Okay. So, initially what will be done when you are starting a process or commissioning a process, then you have no information about the process. So, during that time, to initiate the relay test, what will be done? The Ti, the integral time constant, can be set to certain values, like choose from 10 to 20, when of course, the process GS is stable. So, when GS is a stable process, then at that time please choose or set the value for Ti from 10 to 20, choose any value from 10 to 20, and then you conduct the relay test. Then after conducting the relay test, you will get the limit cycle output, measure the frequency of the limit cycle output, and then you reset, update the value of the integral parameter, and how it will be updated, that we shall discuss after some time. Now, then that updated value of Ti will be put in the integral controller, and again a relay test will be conducted to finally find the peak amplitude and frequency of limit cycle output, and that peak amplitude and frequency will be employed to find the parameters of the PID controller, or basically to find the parameter Kp and Td, and Ti has already been found. Thus, we will be able to get a PID controller, and then we can resume the normal operation of a process. That is how the model free tuning is done. Model free online tuning or model free design of controller is done. Now, I will go to the mathematics of the way we can derive explicit expressions for parameters of the PID controller. Now, when the modified relay is in the loop, let the dynamics of process be described by a transfer function Gs, and that of the controller is GCNS, and of the relay is N. Okay. So, we shall use the describing function for the relay. So, I am using the N for that. Then under limit cycle condition or to obtain a limit cycle condition, the loop gain has to be -1. Then G S G C N S N will be equal to -1. Why that is so? So, if you draw the Nyquist diagram, so this is your Nyquist diagram where we have the real and imaginary, then the limit cycle condition occurs. This is the operating point when the relay test is conducted. So, the net gain will be -1 plus j 0. So, the net gain loop gain will be -1. So, this point corresponds to -1 plus j 0 as you know. Therefore, the loop gain will be equal to G s times G C N S times n is equal to -1. So, we know the form of G C N S. What is G C N S? It is given as 1 plus 1 upon T I S. Then G C N in frequency domain now, G C N j omega will be equal to 1 plus 1 upon j omega T I, okay, which can ultimately be expressed in magnitude and phase angle form as 1 plus j omega T I upon j omega T I, giving us 1 plus omega T I square root upon omega T I with phase angle tan inverse of omega T I minus pi by 2. Okay. So, this is how I get the frequency domain representation for G C N j omega or the integral controller. Now, let me use some function phi. Let phi is equal to tan inverse omega T I. Also, that implies tan phi is equal to omega T I. Okay. Then now, that will enable us to get expression for G C N j omega H 1 plus tan square phi root upon tan phi with angle tan inverse omega T I is of course phi. So, with angle phi minus pi by 2. So, further simplification gives in the numerator sec theta divided by tan theta with angle phi minus pi by 2, which can be simplified as 1 upon sin theta with angle phi minus pi by 2. So, what we have got? The G C N j omega gives us 1 upon sin phi with angle phi minus pi by 2, where phi equal to tan inverse omega T I. So, please keep in mind that the in frequency domain G C N can be expressed by this form. Okay. Now, we know that during the relay experiment the loop gain is -1. So, I have already written, therefore, the loop gain G S G C N S times n is equal to -1, implies in frequency domain now G j omega G C N j omega times n is equal to -1, implies G j omega, the dynamics of the process can be expressed in the form of -1 upon n into 1 upon G C N j omega. Okay. Then what you get? Substitute G C N j omega over here, that will give us now minus sin phi upon n with angle of course pi by 2 minus phi, okay, which again can be expressed as sin phi divided by n with angle. Due to this minus 1, minus pi will appear. So, I can write this as minus pi plus pi by 2 minus phi, and upon simplification you get minus pi by 2 minus phi. So, what we have got? G j omega is equal to sin phi divided by n with angle minus pi by 2 minus phi. Okay. Now, this is what you get during the relay experiment. Now, when the PID controller is injected or put in the loop, when the PID controller comes into picture during normal operation of the system, that time what happens? We will get a new Nyquist diagram. Okay. So, let the controller controlling the process B, GCS is equal to Kp times 1 plus TDS times 1 plus 1 upon TIS. Now, this dynamics, this PD controller will push the operating point from minus 1 plus j 0.2 another operating point, which will be the operating point during normal operation of the closed loop system. Okay. So, the Nyquist diagram for the new operating point will be shown now. So, let this be the Nyquist diagram having real and imaginary parts, and let the plot be given like this. So, we are going from the minus 1 plus j 0 point to some normal operating point of the closed loop system. So, let that operating point, shifted operating point be this one, because you are operating the system with a controller now, and the job of the controller is to get a new operating point such that the phase and gain margins of a system are improved. Okay? That is the objective of pushing the operating point from minus 1 plus j 0 to some new point where you will get improved phase and gain margins. Okay. So, let this be the new operating point at which you will have an unit circle of the form, it is not to the scale, this is the unit circle suppose. Then I will have a phase margin of phi for this one, and corresponding gain margin gives us the magnitude 1 upon xi over here. Okay. So, this is the new operating point due to the controller GCS. So, what you have got, the loop gain here in this case is how much now? It is nothing but simply your GCS GS. So, the loop gain at this is GCS GS. Okay. And the phase margin is having phi and the gain margin is having xi, giving us the magnitude 1 upon xi, minus 1 upon xi at this point corresponding to this. So, little bit of analysis will give you the magnitude for this vector and the phase angle for this vector. So, how this point can be represented? I can represent this point by this operating point is giving us a magnitude of suppose GCS GS will have a magnitude with phase angle of course how much? This is minus pi plus phi. How to find m? How to find m now? So, m can be found if you take the cosine of phi. So, cosine of phi will give you minus 1 upon xi cosine of phi times m, this is the m. So, divided by m, or m can be obtained h minus 1 upon xi cos phi. Okay. So, this is how the magnitude and phase of that point is found. Now, this magnitude, as far as magnitude is concerned, I will have 1 upon xi cos phi. So, the new operating point will give us GC G j omega can be written as 1 upon xi cos phi. This is the magnitude of the vector you have got, and of course, with phase angle minus pi plus phi. So, once you have correctly tracked the new operating point with the phase angle of minus pi plus phi and the magnitude of 1 upon xi cos phi, then further analysis can be carried out easily. Why, how you have got this operating point? I do believe when you have got earlier the operating point here, at that time you had a relay in the loop and you were on the verge of instability, okay? Or I mean to say the system oscillates, or the output of the system becomes oscillatory when the phase is minus 180 degree, and at that time you have got oscillation in the system. So, this point has been pushed to some new operating point with the help of a controller. So, when the controller dynamics is added, you go to this new operating point, and the new operating point results in the phase and gain margins. So, you can easily find the phase and gain margins associated with this with the help of what? The vector, this vector, with the help of this vector. So, as I have said, if the gain margin is xi, then 1 upon xi will be the span over here, and if the phase margin is phi, then you have got the angle minus pi plus phi over here. So, this vector, the new operating point, is denoted by a magnitude of 1 upon xi cos phi, okay, with angle minus pi plus phi. This is very important to get correct expression for the new operating point. Okay. So, after describing all these things, let me proceed with the analysis now. The analysis will be very simple now, because you know the magnitude and phase angle of the new operating point, or when the controller is in the loop. Now, how much will be g j omega from here? G j omega will be equal to 1 upon xi cos phi with angle minus pi plus phi into 1 upon g c j omega. Okay? And what is g c j omega? G c j omega, the controller dynamics in frequency domain is now k p times 1 plus j omega t d times 1 plus 1 upon j omega t I. Okay? This is what you have got. So, g j omega is this much. Okay? Now, I will go to little bit of analysis of this system, like g c g j omega is equal to 1 upon xi cos phi times with angle minus pi plus phi, but g j omega is equal to sin phi upon n with angle minus pi by 2 plus phi. How I have got this one? During the limit cycle, we had put the loop gain to minus 1, and that gave us the expression for g j omega h. G j omega is equal to sin phi upon n with angle minus pi by 2 plus phi. Let me show you, we have already derived that. So, g j omega G j omega is equal to sin phi divided by n with angle minus pi by 2 plus phi minus phi. Okay. So G j omega is equal to minus pi by 2 minus phi. That implies G C G j omega from here. Using that expression, G C G j omega will be equal to 1 upon xi cos phi with angle minus pi plus phi into 1 upon G j omega. Okay. So, substitute the value for G j omega here, which is nothing but sin phi divided by n. So, n will appear here with angle, of course it will go to the numerator. So, pi by 2 plus phi. So, thus giving us G C j omega is equal to n divided by xi times cos phi times sin phi with net angle minus pi by 2 plus 2 phi. Okay. So, G C j omega is found to be this much. So, let me rewrite once more. G C j omega G C j omega is equal to n by xi cos phi sin phi n by xi cos phi sin phi with angle 2 phi minus pi by 2, okay, or the angle is minus pi by 2 plus 2 phi. Further, G C j omega is equal to K P times 1 plus j omega T D times 1 plus 1 by j omega T I, but 1 plus 1 upon j omega T I is how much? That already we have found. Let me show you that how much you have found. So, that is equal to 1 upon sin phi with angle phi minus pi by 2. So, 1 upon sin phi upon with angle phi minus pi by 2. 1 upon sin phi with angle phi minus pi by 2. So, G C j omega is also equal to 1 plus j omega T D times 1 upon sin phi with angle phi minus pi by 2. So, equate the expression for G C j omega, because you have got two expressions for G C j omega. Okay. So, when you equate the two, what do you get? Equating the two will result in equating G C j omega H G C j omega, and writing the both sides now will give us n upon xi time cos phi sin phi with angle 2 phi minus pi by 2. This is equal to K P times 1 plus j omega T D with 1 by sin phi, of course, with angle phi minus pi by 2. Okay. So, what I have done? I am equating this with this. So, equating the right half of this with the right half of this. So, that will give you now further simplification, giving us K P times 1 plus j omega T D is equal to n divided by xi cos phi, okay, xi cos phi with angle, of course, 2 phi minus pi by 2 and then minus phi plus pi by 2. Okay. So, this is equal to n divided by xi cos phi with net angle of phi. So, finally, what we have obtained for the PD controller? The PD controller has to have this much in frequency domain. So, Kp times 1 plus j omega Td has to be equal to n divided by xi cos phi with angle phi. So, Kp times 1 plus j omega Td is equal to n divided by xi cos phi with angle phi. So, please allow me again to find the phase angle of the left hand side in the form of, let phi is equal to tan inverse omega Td now. When phi is equal to tan inverse omega Td implies tan phi is equal to omega Td. Okay? Then this expression in magnitude and phase angle form, because the right half is expressed in the magnitude and phase form, will give us Kp times root of 1 plus omega square Td square with angle tan inverse omega Td is equal to n by xi cos phi with angle phi. Now, substitution of omega Td over here will give you Kp root of 1 plus tan square phi is equal to, with angle phi is equal to n divided by xi cos phi with angle phi. So, that implies Kp into 1 by cos phi. Okay. So, root of 1 plus tan square phi will be sec phi. So, giving us 1 upon cos phi with angle phi is equal to n by xi cos phi with angle phi. So, this will cancel out, this will cancel out, angle will cancel out, angle will cancel out, and giving us Kp is equal to n by xi. So, Kp is equal to, finally, we have got Kp equal to n by xi. What is n? N is the describing function for the ideal relay. What is that? So, n is equal to 4h by pi ap, where h is the relay setting and ap is the peak amplitude of the output signal. Which output signal? Limit cycle output signal. So, you get the final expression for Kp, one of the important parameter of the PID controller H. Kp is equal to 4h upon pi ap times xi. Okay. So, this is how you have got expression for the explicit expression for the parameter of the PID controller. So, Kp is equal to 4h upon pi ap xi. This is the final expression for the parameter of the PID control. What about the remaining parameters? Td is equal to, if you look at what is Td by definition, tan phi is equal to omega Td. So, Td is equal to tan phi by omega. So, Td equal to tan phi by omega. This is the explicit expression for the second parameter of the PID controller. Again, what is the remaining controller parameter? Ti. So, the Ti has got also the expression tan phi upon omega, because we know that tan phi is equal to omega Ti. So, these are the three explicit expressions we have for the parameters of the PID controller. And what are the unknowns we have in the right half of all these three explicit parameters of the PID controller? We have got AP and we have got omega. So, AP and omega are the peak amplitude and frequency of limit cycle output. So, conduct the relay test, obtain the symmetrical output, measure this peak amplitude AP and measure the period Tu, which will give you omega equal to 2 pi by Tu. This is how you obtain the peak amplitude and frequency from the limit cycle output. Substitute over here, substitute in the 1, 2 and 3 and estimate the parameters of the PID controller. This is how tuning of PID controller, model free tuning of PID controller is done. Okay. So, what is phi here and xi here? Let me explain. So, phi and xi are user or operator defined. So, the plant operator or system operator, he decides what will be his phi and xi. Okay. So, phi is basically a value which is greater than the phase margin of a closed loop system. So, analysis will show that phi is greater than phase margin of a closed loop system, and similarly xi is greater than the gain margin of a closed loop control system. So, phi and xi are user defined. So, these are also known. Thus, we obtain the 3 parameters of the PID controller using the formulae given over here, which uses the user defined parameters xi and phi, and which also uses the parameters obtained from the limit cycle output such as peak amplitude and frequency. So, we will go to simulation study now, and before going to the simulation studies, let me once more explain the steps for the automatic tuning of the PID controller without finding transfer function models for the dynamics of a system or process or plant. So, auto tuning test starts with the initial choice of TI, which is between 10 to 20 for stable processes. Okay? For unstable processes, you have to check what suitable values you have to choose for that, when you have no information available for the process dynamics. But once the process is in operation, this parameter can easily be obtained because you can use the default value. Okay? Now, TI is updated for a user defined phase angle of phi greater than equal to 30 before beginning the second stage of relay test, using the updation formula. Of course, TI is equal to tan of 30 degree or greater than equal to 30 degree upon omega. So, omega is the frequency you obtain from the first test, substitute over here, then find TI, substitute TI while conducting the second stage of relay test. Amplitude AP and frequency omega of the limit cycle output are measured in the second stage of the auto tuning test. Okay. So, those values will be used in the formula to find the PID parameters, and the parameters of the PID controller are then obtained from the set of the formulae for a chosen value of xi and phi. Okay. Fine tuning of the controller, if necessary, can be done with different user defined phase angles phi. Okay. We will go to the simulation study now. Consider a second order plus dead time process dynamics given by Gs is equal to e to the power minus s upon s plus 1 square, with the initial choice of Ti is 20 seconds and h the relay setting of h equal to 0.5 relay test is conducted. How this the simulation diagram is given. So, the relay setting is plus minus 0.5, then a PI, not PI, I controller H 1 plus 1 by 20 s, which gives you 20 s plus 1 divided by 20 s is employed for the process and relay test is conducted. Then the critical frequency found or the frequency of oscillation is found to be 1.2925 radian per second, and choosing a phase of 30 degree, TI is now updated to 0.4467. How do you get this TI? As I have said, TI is equal to 10 30 degree divided by omega. So, 1.2925, this will give you TIH 0.4467, and then another relay test is conducted. So, another relay test is conducted further, where the I controller is now 0.4467 s plus 1 divided by 0.4467 s. Okay. Then the test yields a critical frequency of omega is equal to 0.6575 radian per second. So, this is the final value we will be using in the formulae for PID parameters. Amplitude of the peak amplitude of the output is of the magnitude 1.602. So, omega is 0.6575 and AP is equal to 1.602. Then the TI is calculated using the formula TI is equal to cos 30 degree, sorry, tan 30 degree divided by omega. So, 0.6575 giving us TIH, TI is equal to 0.8781. Thus, the TI, one parameter of the PID controller is finally estimated. Then the remaining parameters are calculated as Kc is equal to 4h divided by pi AP xi, where xi is the user defined value. We have chosen a gain margin of xi is equal to 2. Okay. So, Kc is equal to 4h divided by pi AP xi is equal to 4 into h is 0.5 divided by pi into AP is 1.602 and xi is 2, giving us Kph, sorry, not Kc, Kph, Kp is equal to 0.1987. Okay. And the other parameters Ti, which is equal to Td, as the expression for both are same. So, Ti is equal to Td is equal to 10 phi divided by omega is equal to 10 30 degree divided by 0.6567 is equal to 0.8781. So, Ti is equal to Td is equal to 0.8781. Thus, all the parameters of the PID controller are estimated. Let us see what sort of result we get from the PID controller, how the PID controller performs. So, a simulation diagram is employed to see the performance of the PID controller. This is the process, your GS. Okay. So, the process dynamics is now GS is equal to e to the power minus s divided by s plus 1 square. This is what we have considered. Please keep in mind, we are using a process GS is equal to e to the power minus s divided by s plus 1 square. So, the process is there, this is the process. Now, the controllers are present here. Now, we have got the controller 1 plus 1 divided by 0.878781 s, which is given in this form, is presented. Okay. And gain of Kp is found to be 0.1987, and the PD controller is realized here. If you carefully see, observe, then what you have got from here, it is nothing but 1 plus TDS. This is realized using the derivative block with the gain, and you have of course 1 plus TDS realized by this. So, the series form of PID controller is employed now for the system GS, given by GS is equal to e to the power minus s upon s plus 1 square. So, the PID controller is now GCS is equal to 0.1987 times 1 plus 1 divided by 0.8781 s times 1 plus 0.8781 s. Okay. So, this PID controller is employed now. So, whole PID controller is from here to here. Please keep in mind, this is the PID controller. Okay. GCS can be realized in this form. Then a unit step is applied at time t equal to 0. Unit step is the reference input. Okay. And a step load disturbance of magnitude 0.5 occurs at time t equal to 40 seconds. So, the system is subjected to a static load disturbance of magnitude t equal to 40 seconds. Then what sort of performance we get? This is the response we are getting. So, the closed loop response to step input and load disturbance is shown over here. So, we have got quite satisfactory time response for the closed loop system, of course, with the PID controller using the model free controller design technique. Okay. Why I am telling we have got quite successful or quite useful response, time response, because the rise time and settling time, the two important parameters associated with the time response of a process are found to be satisfactory. So, rise time and settling time are less, okay. And the disturbance response is also satisfactory, because the disturbance, static load disturbance magnitude L is equal to 0.5. So, we have got satisfactory reference input as well as load disturbance rejection from the closed loop system. Now, to test the robustness of the method, it is assumed that there are plus 10% variations in all parameters of the process. That means, the process was GS was e to the power minus s upon s square plus 2s plus 1. I have varied the different parameters. The steady state gain was 1. I have made it to 1.1. The delay is made to 1.1 seconds. Then the time constants, due to the variation in the time constant, I have got 1.21 s square plus 2.2 s plus 1. So, this is the perturbed plant. So, assuming plus 10% variations in all parameters of the process, now we will see the response we get a performance given by the dashed line. Okay. So, this is the response we get from the perturbed plant. So, the two responses are not different, not significantly different from each other, giving us or informing us that we do get robust responses provided by the PID controller. Okay. So, let me summarize the lecture now. We have discussed a method for tuning of PID controllers without using parametric model of a process dynamics. Directly we have formulated some tuning rules based on the limit cycle parameters. So, Kp, Ti and Td are now functions of Kp, Ti, Td. All the three parameters of the PID controller are functions of peak amplitude and frequency of the limit cycle output and user defined xi and phi, the phase and gain of a system, gain margin of a system. The model free control technique is also found to be simple and robust. It does give robust performances because the design is based on fetch and gain margins. Let us come to the point to ponder. Any guideline we have for choosing the fetch and the gain values? Generally, it has been found from analysis that the gain margin of the loop, gain margin is found to be greater than the user defined xi, and the fetch margin is similarly found to be greater than phi. Therefore, one can choose xi to be greater than equal to 2 and phi to be greater than equal to 30 degree. That will give not only robust performances, rather satisfactory time domain specific performances also for the closed loop system. Thanks.